So we're really close to the end. And so let's recall what we're doing. We're in the last part of the course. We sort of had this row map we've been following, which says our goal is to approximate functions. We start by saying, hey, let's start by talking about a large collection of numbers. We called that sequences. And then we said, well, let's add all those numbers up. And that was series. And we spent a lot of time saying, okay, well, when does it make sense to add up a lot of numbers? And so we spent a lot of time on that. But let's not forget, that was just a part of our journey. Because what we really wanted to get up to is power series, which now, what do we have? Well, it's series of functions, but really what you have here is you have this big infinite polynomial. And finally, we're coming to our last major topic. It's not our last lecture, because we're going to spend some time talking about this, but it's our last major topic, and that's called Taylor series. And the idea is, hey, you know what? For some functions, not every function, but for some functions, we can make it look like this infinite polynomial. In other words, we can replace our function by something which is easier to work with. Because polynomials, they're our ideal things. So, we're ready to talk today about our last stop on our roadmap. So let's talk about approximating functions, because that's what we're after here. In particular, we're talking about approximating a function at our point x equals a. And a can be any value we want. It just depends on the particular problem that we're working on. All right, well, let's just say, suppose I wanted to approximate it by my best constant. In other words, I want to say, what value should I pick so that if I were to pick a constant, then the function is mimicking what's happening at a as best as possible? Well, the answer is just choose f of a as the constant. Because it is true that f of x is approximately f of a near x equals a, at least for any reasonable function. Now you might say, okay, that doesn't seem like a very good approximation, and it's not. We can do better. So one of the first things we said in calculus was that, hey, we can do what we call the linear approximation. Of course, we have a better name for it. We call it the tangent line. And so the way we do that is we take our function f of a plus f prime of a times x minus a. So this is our tangent line. You'll notice that these match in the first term. Then there's this extra piece here. Now the way you should think about what this best linear approximation is doing is it says, I want to mimic what the function is doing at a. Now when you have a line, you essentially get 2 degrees of freedom. And so what we're going to have is we're say, look, the way we're going to say it matches what the function does at a is we're going to say it has the same value of the function at a, and it has the same value as the derivative at a. Well, okay, why stop there? Well, what would be the best quadratic approximation? You know, the quadratic that is most closely approximating what the function is doing. The answer is it's going to be f of a plus f prime of a times x minus a. So if you were to cover that up, that's your tangent line, plus a little bit extra. So f double prime of a times x minus a squared over 2. Now what does that little bit extra give us? Well, that little bit extra is giving us the following nice property. We're going to match what the function does with the function at a, the derivative at a, and the second derivative at a. So in other words, our best quadratic approximation is trying to get to saying, let's try to mimic as many derivatives as we can, of course realizing that if you have a quadratic, you have at most 3 degrees of freedom. Now you might be wondering, where is that 3 coming from? Well, a quadratic says you have ax squared plus bx plus c. That's what I mean by a quadratic. So you'll notice I have 3 things I can play with. If you like, 3 levers I can pull. A, B, and C. And so I get to control a little bit, but not everything. And so the question is, okay, given that I have these 3 choices, I get to make 3 decisions. So that's why our decisions are, let's match what the function does at a, the derivative of the function does at a, and the second derivative of the function does at a. So let's see how this does. So we'll do some examples here. All right. So we're going to give the quadratic approximation to f of x, which is e to the minus 2x at x equals 0. So we should start by saying, well, let's take the derivative and the second derivative, because that's what we're trying to match. Now the first derivative, the negative 2 comes down, that's minus 2 e to the minus 2x. And then the second derivative, that would be 4 e to the minus 2x. Okay, so what is our best quadratic approximation? Now, just for reference, I have it where I can see it. I'm going to just point it to it again. It's this part right here. We're going to talk about why we need a 2 later on. So I'm going to say, okay, I know what my choice for A is, so I'm going to plug it in and just fit it into my mold. So this is at x equals 0. So in other words, this 0 is my choice for A. So we can say that e to the minus 2x is approximately, plug 0 into the function, e to the 0 is 1. Now, let's come down to this picture here, because I want to explain what this picture is. It sort of looks like some sort of minimalist modern art, but it actually here represents something. So you have your axes, and this dotted line along here, that's the actual function. That's my e to the minus 2x that I'm trying to approximate. This blue line would be if I were just to use the constant. Now you can tell I match pretty well there, but not very well as soon as I start drifting out. All right, but that's okay, because now we go to our next term. So we say, okay, take f prime at 0. Well, that would be minus 2. And then we're going to times that by x minus 0. So that's minus 2x. So if you come to here, 1 minus 2x, that's the tangent line. That's this green line that you see here. And if you look, comparing the blue line to the green line, you can see that the green line, it does a little bit better job. In fact, it kind of seems to, it seems to be doing, roughly a little bit better. See, the blue only seems to match right around there. The green, a little bit further along. Now, what if we go into our quadratic, our second derivative? Well, so we plug our second derivative at 0. That would be 4. And remember, there was that over 2. We'll come back to that. So you would have plus 2x squared. So if you were to take that, that is our quadratic approximation, and that's the red line. Now, how well does this do? Well, you'll notice it actually does pretty well. It's closer to a larger extent. So what's happening here? Well, the better we sort of mimic what the behavior is at that point, at 0, then it seems to be that the closer we are nearby. In other words, we're doing a better job of approximating the function in the neighborhood. And this is one of the things we sort of set out to do in Calc 1. We said, we want to get an even better way to approximate, and this is our better way. So the more we match behavior at that particular point, the more that we follow what the curve will do as we move out from that point. Now, of course, this is just quadratic. Well, can we do better? Yeah, we'll get there. We'll get there. All right, how about another function? Sine of x plus cosine of x. And now we'll do it at pi halves. Okay, so let's start by taking some derivatives. So f prime of x, the derivative of sine x plus cosine x, derivative of sine is cosine, derivative of cosine minus sine. Second derivative, derivative of cosine minus sine. Derivative of minus sine is minus cosine. So we have that sine of x plus cosine of x is approximately, okay, here we go, let's work our way through it. So we're at pi halves. So we're going to plug pi halves into our expression. Sine of pi halves is 1, and cosine of pi halves is 0. So we get 1. So that right there, again, the dotted line here that you see, that's the actual curve. That's the sine plus the cosine. This line here, that would be if we only used our constant as our approximator. Again, only good very nearby. Almost immediately, it becomes pretty bad. Okay, well now we go to our next layer. So what's our next layer? Well, now we're going to plug pi halves into the derivative. So we need to evaluate. Because if you go back to our expression, if you look here, it's not f prime of x times x minus a, it's f prime at a. So in other words, we're doing our evaluation. So what do we have? Well, we're going to get cosine of pi halves, which is 0, minus sine of pi halves, which is 1. So 0 minus 1. So it's a minus, and now x minus a. There we go. Now, that's our tangent line, or if you like, our linear approximator. And again, you can see it's a better approximation. It more closely mimics the function than if we just were to use the constant. But can we do better? I think we can. Our second order approximation are the quadratic. Okay, again, plugging in pi halves. Sine of pi halves is 1, cosine pi halves is 0, minus 1 minus 0 makes again a minus 1. And so remember there's that over 2. All right, we'll talk about that. We'll talk about it. So, oops, I should have marked. Ha ha ha. There's our line, and then there's our quadratic. So that's our quadratic approximation. But again, if you come down here, so we've marked in red what the quadratic approximation is. And if you look, it actually does a pretty decent job. So in other words, it's doing a much better job than our tangent line is. So the more that we use, in other words, the more information that we have about our function, the better the approximation should be. Now at this state, you should probably say, well, if I use more, I get better, then, well, why shouldn't I just use everything, right? Well, that's a great idea. In fact, we can do that. So why stop? We can keep going. So what we have is we're going to start with what we call a Taylor polynomial. So we call it the nth order Taylor polynomial, or if you like, the nth order approximation. And what we do is we say, look, our function is f of a plus f prime of a times x minus a plus dot 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 plus the nth derivative of a times x minus a to the n over n factorial. Or if we use our notation for sums, the sum k equals 0 to n of f. Okay, now this notation here, that means the kth derivative, because, you know, you wouldn't want to write down, hey, I'm going to take the 17th derivative. That takes too long. I don't even know if there's 17, you know. But if you certainly had to say which one is more understandable, you're like, yeah, definitely the second one is more understandable. So that's the notation. X minus a to the k over k factorial. And all right. Well, so why k factorial? Now comes the part where we say, remember what happens when we take derivatives. Every time we take a derivative, the exponent comes down. And so what we want to do is we want to put something downstairs that's going to compensate for bringing these exponents down. And that's why we need that k factorial. Because at first, you're going to get a k down. Okay, that can factor off with the first k. The next time we bring a k minus 1. Okay, that factors with the k minus 1. Because remember that k factorial really is k times k minus 1 times k minus 2 and so forth and so on. And so what's going to happen is after you take k derivatives, what will end up happening is that this term right here will be gone. And you're just going to be left with that fk at a. So, what's the story here? And once you understand the story, everything else makes sense. The story is that the larger the value of n, in other words, if I want a better approximation, the more we match the derivatives of the original function, and that's the better the approximation. And we're going to be really explicit here. I should add this comment. We're going to match at our point x equals a. So we're really trying to say our goal is to find a polynomial which behaves as much as we possibly can as far as it goes to how the function is behaving at the point a. And where as much as it can means with respect to derivatives. Now I think it's good to walk through what's happening. So there's the claim that this is the best, and the best by matching polynomials. So let's suppose we have some really explicit things. So I have my function f of x, and here's my polynomial. So this g of x is my Taylor polynomial. So it's f of 0, f prime of 0 over x times x over 1 factorial, f double prime of 0 over x over 2 factorial, f triple prime of 0, x cubed over 3 factorial. Now, suppose I plug in 0. So I haven't actually done it. What happens? Well, notice what happens to all the terms with x's. When I plug in x equals 0, anything with an x disappears. So what doesn't have an x? Well, the answer is f of 0. All right, well that's nice. So now let's take the derivative. You'll notice that the f of 0 is a constant, so that term goes away. The x over 1 factorial, well that's x, the derivative of x is 1. So I have f prime of 0. Derivative of x squared. The 2 comes down, cancels with that 2 factorial, so you get left with just 1 factorial. So it's x over 1 factorial. Here, 3 comes down. 3 over 3 factorial becomes 2 factorial. So that's what happens when we take the first derivative. What happens when we plug in 0? Well, that term vanished. These terms have x's, so g prime of 0 is f prime of 0. Everything else goes away. All right, how about the second derivative? Well, okay, so that term, f prime of 0 is going to be gone. Here, derivative of x is 1, so it's f double prime of 0. In the last term, derivative of x squared over 2 factorial, the 2 comes down, so you'll be left with x over 1 factorial. We plug in 0, and what do we get? Well, the last term is going to be 0. The first terms have fallen out, so g double prime of 0 is f double prime of 0. Finally, you'll probably see there's a pattern here. Take the third derivative. The derivative of x is 1. Everything else goes away. So we get that the third derivative of the Taylor polynomial is actually just the third derivative at 0. And therefore, the third derivative of the Taylor polynomial at 0 is simply f triple prime of 0. So that's what we mean when we say that this polynomial is the best, because it's matching the derivatives. It matches the first derivative, it matches the function itself, the first derivative, the second derivative, and the third derivative. In other words, it's matching exactly what the function is doing at 0. And that's why we say this is a great approximation. So those are our Taylor polynomials. So this is a way that we can get a nice polynomial approximation. And oftentimes we're usually satisfied if we just say, let's take the Taylor polynomial to the second or third term. But you might say, what if I want to get the best approximation? Well, the larger the value of n is, the better the approximation. And so the best one should be, hey, let's let this n get huge. And in particular, let's let it go off towards infinity. Well, as you let n go to infinity, what happens is a polynomial becomes a series. Because we think of our power series in particular as sort of an infinite polynomial. And so we have that this is our Taylor series. And so in particular, to be explicit here, this is the Taylor series, and this is for the function f of x at the point x equals a. All right, so that's our final stop along our way. We've reached our destination. Now, what's the goal? Our goal is to say this is a great approximation. And we're going to discover that for many functions, it truly is a wonderful and fantastic approximation. So good that it's going to match the function over some range, sometimes for all values of x. But that's a story we're going to get more into in the next lecture. But for now, let's try our hands. All right. Find the Taylor series for f of x, which is e to the x at x equals 0. So what's our goal? Well, we need to know where our center is. Well, that's given to us. So our center is at 0. And so we have that, we're going to have that the sum k equals 0 to infinity of the kth derivative evaluated at 0 times x minus 0 to the k over k factorial. Now, in some sense, this last part, there's nothing for us to do. That's just the form. So what do we have to do? Where's the work? Because there must be some work involved, and there is. It's in the first part, this fk at 0. So what we need to figure out is what's the kth derivative at 0. So we're going to take a look at this function. So we'll start here, f of x, that's e to the x. The first derivative, and I'm just going to go ahead and adopt the notation f1 of x. So remember that means the first derivative. That's derivative of e to the x is e to the x. The second derivative, well, what's the derivative of e to the x? It's e to the x. How about the third derivative? Okay, what do you think? Yeah, you're right, e to the x. In fact, I suspect we see a pattern here. Hopefully you see it by now. What's the kth derivative of x? Well, it's e to the x. And therefore, we see that this function, e to the x, it's really, really beautiful. Now, we're not going to put in the kth derivative at x. We need the kth derivative at 0. So, the next thing for us to do is evaluate these at 0. E to the 0 is 1. So what we're going to end up with is that every derivative, when we evaluate it at 0, is always 1. All right, so that's a nice property of e to the x, namely that it doesn't matter which derivative you take, no matter which one it is, when you evaluate at 0, you always get 1. So what we end up with is we get the sum k equals 0 to infinity. This is 1, and then you end up with x to the power k over k factorial. So this is our Taylor series for f of x. Now the theory says e to the x is approximately this sum. K equals 0 to infinity x to k over k factorial. But, fun fact, and we'll get to this again next time, it turns out that this is a really good approximation. In fact, it's the best approximation in the following sense, that e to the x is actually equal to the sum. All right. So this is a way to compute e to the x, or at the very least, it's a good way to approximate e to the x for any value of x. Okay, so that's the Taylor series for e to the x. Good. And by the way, I put a single box around this, but that truly underestimates how important that this is. This fact is ultra super important. It deserves multiple boxes, maybe even a squiggly line in one of the layers of the boxes. And maybe we should shade it with some nice color here. So this power series, or this Taylor series for e to the x, it's ultra super duper important. Like, you really want to know this one. This one is one you should know by heart. And it's after the geometric series. This is probably number 2 on the list of things that you should know. All right. Well, let's, how do we use it? So, here's what we're going to do. Next one. Find the Taylor series for f of x equals x squared e to the x cubed centered at x equals 0. Now, at this point, you're probably going to say, uh-oh, that seems hard. Because, well, there's this x squared, this e to the x cubed. When I start taking derivatives, I'm going to have some power rules. I'm going to have product rules. I'm going to have chain rules. That seems complicated. So let's just step back and say, we're not going to do that, all right? So, good news. Here's sort of our philosophy. If we find a series that works, then it turns out it is the series. Now you might say, what does that mean? Well, we're after a Taylor series. So in other words, we're trying to find a series that's approximating this function. So if we can find a series, there's only one that works. It has to be the series. And why is that true? Well, in some sense, what you should think of it is think of it in terms of polynomials. We're after this infinite polynomial, the infinite polynomial that's approximating this function. If I find an infinite polynomial that does a good job of approximating this function, then it has to be the right one. Because two polynomials are going to be equivalent. Because, well, in essence what it is I can't have two polynomials doing the same thing unless they're the same polynomial. Okay, so that's sort of one idea. Now, the second idea is I want to go back to the Taylor series for e to the x. So that is idea number 1. And the second idea is modify what we know. In other words, don't reinvent everything the first time you encounter it. We don't want to have to redo everything over and over and over again. Why? Well, that's work. Our goal is to make life easier, not to make life more challenging. We want to make things simpler. So we don't want to keep redoing the same work over and over and over again. So, okay, so how does that work? Well, what we're going to do is we're going to say, all right, let's start with the e to the x cubed and think about how we can get that. See, the x squared, that we like. The x squared is nice. Why do I say it's nice? Well, the x squared, it's polynomial. And so that's why that's nice. When you're after a Taylor series, you're essentially after some big polynomial. So we like things that look polynomial-esque. So, all right, so I need to work with that e to the x cubed. I want to make that look like a polynomial. So I start by saying, well, let's start with what we know. So we have for e to the x, it's approximately, again, it's not really an approximation, but we'll get into that next time. Sum k equals 0 to infinity, x to the k over k factorial. You know what? I'm just going to embrace it. I'm just going to say it's true. This, in fact, is equal. All right. Now, I want to rewrite this. I'm going to say e, but not with x. I'm just going to say to the box is equal to the sum k equals 0 to infinity of something to the k over k factorial. Now, our question becomes, what's in the box? See, this is a mold. And once you can understand, it's like, oh, I'm just trying to make things fit my mold, then things become a lot easier to work with. Now, in our case, what we have is that what we're putting into e is x cubed. So we say, well, f of x, that's our x squared, e to the x cubed. Again, x squared, we're okay with it for now. We'll just leave it as it is. And then we have our e to the x cubed. That's where we apply our mold, where this input is x cubed. So we're going to put that into there. So if I put x cubed here, I put x cubed there. So I'm going to have the summation k equals 0 to infinity of x cubed to the k over k factorial. All right. Well, that's what? I'll put the x squared here. Summation k equals 0 to infinity x to the 3k, because to the 3 to the k, multiply the exponents, over k factorial. Now, our last thing is, if this is a polynomial, I can multiply this inside. So I'm going to multiply x squared into every single term. There's actually infinitely many terms, one for each value of k. And so doing that, we get that this is the summation from 0 to infinity of x to the power 3k plus 2 over k factorial. And that is the Taylor series for x squared e to the x cubed. It's actually a really simple, nice form. All right, well, interesting. So suppose my function is x squared e to the x cubed. Like that. Find the 50th derivative at 0. Well, if we were in Calc 1, we would probably be like, this is going to take us forever. And we'd be right, because the only thing we could do is like, well, start taking derivatives, cross our fingers, and hope we either spot a pattern soon, and if we don't, just grin and bear it and take 50 derivatives, and hopefully we don't make too many mistakes. And by the time we reach the end, then we'd be like, okay, well, that's the answer. But we don't want to do that, because our goal is to say, hey, there's got to be a smarter way. And what's our smarter way? Well, remember, we found a series. So this is the series. Okay, so this is the right series for that. In other words, this is the Taylor series for x squared e to the x cubed. But what is the Taylor series? Well, so the Taylor series, I'm going to use a slightly different index, just so instead of k, I'll just change it to j. Just so I have a j equals 0 to infinity of, you take the jth derivative, evaluated, and we're at 0, times x minus 0 to the j over j factorial. And I'm going to write that, just clean up just ever so slightly, 0 to infinity of the jth derivative evaluated at 0 over j factorial times x to the j. Now that is what our Taylor series is. Okay, that's our definition. We should, of course, be careful. What does this mean by equals? And we'll get into that next time, what we mean by equals. It certainly definitely is equal at 0. Oftentimes it's equal in a slightly bigger neighborhood. It just depends on our function. Okay, so on the other hand, we also have that this is equal to the summation from k equals 0 to infinity of, and I'm going to write this here as 1 over k factorial x to the power 3k plus 2. Now, here's the great and you got to think about this for a few minutes to convince yourself that what we're about to say is true. So, all right, let's go through it carefully. These two series represent the same thing. They are the approximation to our function x squared e to the x cubed at 0. And okay, so that means that they have to match. So these two series here have to be the same. Now, when do two series match? Well, it's the same question as when do two polynomials match. So the key here is that the coefficients, in other words, if you were to write these series all out, they all have to be the same. Okay, so that's cool. So what coefficient do we care about? Well, now we come to it and say, I'm after some coefficient that has this piece. Well, in this format, there's nothing to do with derivatives. So I'm looking up here, and I say, well, what coefficient has the 50th derivative at 0? And, well, if I want the 50th derivative, I want j equals 50. So that would be x to the 50. So here's the idea. I don't need to look at all the coefficients, so let's look at the coefficient of x to the 50th. And let's see what that is. So in the first sum, on the, we'll call this the top sum, if we plug in j equals 50, we're going to get the coefficient of x to the 50th is the 50th derivative at 0, divide that by 50 factorial. On the other side, what are we going to get? Now this one you have to be a little bit more careful about. So remember, I'm not saying, look, say the 50th thing that showed up. I want the coefficient for x to the 50th. So we've got to be careful. Right now we have 3k plus 2. So when does 3k plus 2 equal 50? Well, I would say 3k has to equal 48, because I can subtract 2. And now I can divide by 3, and that says k equals 16. So for that sum, we're going to look at k equals 16. I do get x to the 50th, and the coefficient I get in front, in other words, the number in front of there, is 1 over 16 factorial. Okay, so now we have that the 50th derivative at 0 divided by 50 factorial is 1 over 16 factorial. So our conclusion is if I just want the 50th derivative at 0 by itself, multiply it across, that's 50 factorial divided by 16 factorial. And we're done. We actually found it. Now, what's this number? It is ginormously big. In fact, if you were to multiply it out, it's more than the number of particles in the universe. It turns out this is 50 times 49 times 48, and you keep going all the way to 17. That's what that number is. It would be massive. If you were doing this without any computer, you would not be able to multiply these numbers out without making an arithmetic error, or you were using a lot of coconut technology and you had a lot of time on your hands. Maybe you were on a desert island somewhere. But that's the right answer. That's exactly the right answer. And you'll notice we really didn't have to work at it. Why did we get to sort of make our life so easy? Well, because we had a more powerful tool. We were saying, hey, instead of computing a single derivative, which is, we're after the 50th derivative, in essence, we have all of the derivatives. So this expression here, this right here, and I'll point it over here. This is storing all derivatives of the function f of x at x equals 0. In other words, the first, the second, the third, the fourth, the hundredth, the millionth, the billionth, we found them all. We channeled our inner Pokemon, got to get them all, And we did. And then we were saying, hey, since we have them all, I can casually just check to say what happens to the 50th derivative. So now we can ask ourselves about any derivative we want. For instance, we could say, well, what about, I don't know, the 100th derivative at 0? What would that be? Well, what would it be? Now notice, if I wanted x to the 100, what would happen? Let's do that computation here. So what if I wanted to have 3k plus 2 equal to 100? Well, that would say 3k has to equal 98. Well, wait a second. 3 doesn't divide into 98. So you end up with 98/3, which is not a whole number. But this value for k only takes on whole numbers. 0, 1, 2. So what does that mean? Well, it means that there's a gap. So there is not an x to the 100. So, well, actually there is. There secretly is. So if there's a gap, you don't see an x to 100, what does that mean? So it means that the coefficient of x to the 100 is 0. And therefore, that says that the 100th derivative at 0 is 0. And that's it. So really, now we can find, again, all the derivatives of this function at 0, and we get it with very little work, because we found them all. So that's good. All right, so this e to the x, we're going to do a lot of work with that, but we want to start building up our library. So we have e to the x, and so the next one we're going to add to our library, we're going to do sine of x. Okay, so find the Taylor series for sine of x at x equals 0. All right, well, how do we do that? Well, we say, look, the Taylor series is going to be the summation k equals 0 to infinity of the kth derivative evaluated at 0 times x minus 0 to the k over k factorial. So I'm just taking our general Taylor series at x equals a, but I'm replacing a by 0. So I can write that as the sum k equals 0 to infinity as, well, I'll put it as f, k derivative at 0 over k factorial x to the k. So the key here, it's the same key as what we had before, is look, I really just need to figure out what's happening to the derivative at 0. So I need to look and figure out what that's doing. So we're going to spend some time here and see if we can spot some patterns. So I think it's going to be a little bit more flavorful than what we had before. So the function is sine. What's the first derivative look like? Well, derivative of sine is cosine. How about the second derivative? Oh, I know that one. Negative sine. Derivative of the third derivative, right? Derivative of negative sine, negative cosine. All right, well, how about the fourth derivative? Well, that'll be negative cosine, which is positive sine. How about the fifth derivative? Well, that's back to cosine. How about the sixth derivative? Well, that's negative sine. How about the seventh? Okay, well, that's negative cosine, and so forth and so on. Now, in general, what we have to be careful of is we're not always getting the same function. But you see, it's not changing too much. We see sine, cosine, negative cosine, then back. Sine, cosine, negative cosine. So what's going to happen is it's going to end up repeating every 4 times. So in general, we get that the derivative here, the kth derivative of x, well, it's one of 4 possibilities. It's either sine, cosine, negative sine, or it's negative cosine. Now, which one is it? Well, it depends on where we're at. So if we don't take any derivative, it's sine. If I took 4 derivatives, I'm back to sine. So if I took 4 more, so 8 or 12 or 16. So that says if I'm really a multiple of 4. So if k is a multiple of 4, I'm sine. To get to cosine, well, that'd be 1, 5, 9, so forth and so on. So that would be if I was a multiple of 4 plus 1. How about negative sine? Well, that's plus 2, shifting by 2. So that's a multiple of 4 plus 2. And negative cosine is a multiple of 4 plus 3. Okay, so that's the pattern. We repeat every 4 times. Do, 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 do. Now what? Well, that is not what goes into here, because remember, we have to evaluate at our point. So we need to evaluate at 0. So the next thing for us to do is let's plug 0 in. So our kth derivative evaluated at 0 is, well, depends where we're at, right? So if I plug 0 into sine, sine of 0 is 0. So that's if I'm a multiple of 4. Cosine of 0 is 1. So that's if I'm a multiple of 4 plus 1. Negative sine of 0, well, it's negative 0, but we usually just write that as 0. So that's if I'm 4l plus 2. Negative cosine of 0, well, that would be minus 1. That's if I'm a multiple of 3. All right, so we see this pattern. 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, dot, dot, dot. So let's write that down. Let's sort of start writing our first few terms. So you'll see that the even numbers are going to be zeros. So, for example, x to the 0, that's going to have no coefficient. So our first term is 1, and that would be, so 1 over 1 factorial times x. Then for 2, we get 0. For 3, it's a minus 1 over 3 factorial x cubed. 4, back to 0. 5, a plus 1 over 5 factorial x to the 5th. 6 is 0. 7, a minus 1 over 7 factorial x to the 7th. 8, back to 0. 9, plus 1 over 9 factorial x to the 9th. 11, well, what would that be? Well, first off, 10 is 0. 11 is a minus 1 over 11 factorial x to the 11th, and so forth and so on. So, dot, dot, dot. Let's pause for a second here, because there's a kind of a cool fact we should say, ooh, isn't that interesting? Now, what do we know about the sine function? So a little side note. Let's see. We'll put it down here. Sine is an odd function. Well, why do I make that note? Notice, what do we see on our powers here? To the 1, to the 3, 5, 7, 9, 11. What's true about all those numbers? All of them are odd numbers. Now, what do you think? Coincidence or not coincidence? The answer is not coincidence. So whenever I'm looking for a Taylor series, if I have an odd function, I'm only going to get odd powers. If I had an even function, what do you think should be true? That's right, we're only going to get even powers. So that's a good sign. It means something must be true here. Well, let's find a way to write this in sort of a nice compressed format here, because we don't want to have to, write it out this way. Our goal when we write for power series is to really find a compressed format. So in other words, a single sum. One sum that will bring all these terms together. One sum to rule them all. So how do we do it? Well, we say to ourselves, all right, what's happening? Well, it's a lot like what we saw before. We have, what do we have? Well, we have alternating, right? Plus, minus, plus, minus, plus, minus. So I could write this as a sum, and I'll still use k. It's not the same k here. 0 to infinity. When I see anything alternate, plus, minus, plus, minus, plus, minus, that tells me I have a minus 1 to the k. Now, how about my powers? Well, my powers are 1, 3, 5, 7, 9, 11. So I want 0, my first term corresponds to 1. The next thing, 1, should be 3. 2 should be 5. 3 should be 7. In other words, I want it, not that k equals 0 is the power of x, but rather it's the sort of the kth term showing up that I have to keep track of. So how do I do that? Well, you'll notice I start at 1, then every time I add 2. So that would be x to the power 2k plus 1. Now what's the last thing? Well, I have a factorial downstairs. But you'll notice that the factorial matches the exponent. So 1 factorial, 3 factorial, 5 factorial, all the way down. They're matching, 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 matching. So that can be written as 2k plus 1 factorial. And you'll see this is the right pattern. It captures everything. All right, so that is our Taylor series for sine. Now, should you know this one? Yes. Yes, it's very, very nice. It's actually a really, really beautiful thing. You'll notice it kind of has a similar feel to what you have for e to the x. In particular, we see e to the x, you have like x to the power divided by a factorial of that power. What's the difference? Well, there's two differences. One, you see this altering, plus, minus, and well, the other difference, of course, is it's every other term. So, but other than that, they're very close, which means that probably there's a nice connection between e to the x and sine of x. And there is. There's actually a really beautiful connection. We're going to get to that soon, in the near future. So this is something we should know. So we'll again, look how much time we're spending on decorating this. You know, if I was a better artist, I'd be drawing little unicorns and all sorts of stuff. Now you might be wondering, saying, okay, Steve, that's the Taylor series for sine x. Is it any good? It's fantastic. True fact, and again, we'll talk more about this next time, it's not just a good approximation, it truly is the best approximation. Sine of x does equal that for any choice of x. Okay. Well, if we're going to do sine, let's do cosine. Now, you're probably thinking, we got to go through all that again? But no, remember, that's not our goal. Our goal is to say, let's make life better for ourselves. Let's make it easier. And so, how do we make things easier? Well, we ask ourselves the question, can I take what I already know and find some way to use that information to find what I don't know? So I know something about sine. Can I take sine and do something simple to it to produce cosine? Now, if you're just thinking trivial, like, well, I could take the square root of 1 minus sine squared. No, come on. We're in calculus. Is there a calculus thing you can do to sine and get to cosine? The answer is, there is a calculus thing you can do. You can take the derivative. So, we're going to take the derivative. And remember, one of the things we did last time was we said, we can talk about derivative of these power series. So we can say, look, the cosine of x, that's the derivative of the sine of x. So that's the derivative of the sum, k equals 0 to infinity, of minus 1 to the k. Divide that by 2k plus 1 factorial, x to the power 2k plus 1. And we'll do this a little bit slowly. And the moral here is where this converges, and it's for all values, but that's a story for next time. I can pass the derivative in to the sum. But what's the derivative of x to the power 2k plus 1? Well, it is the following. Whoops, sorry, it takes a while to write all this down. 2k plus 1 factorial. The 2k plus 1 comes down. X, 2k plus 1 minus 1. And, okay, I'll go ahead and write that out. But of course, if you take 2k plus 1 minus 1, you see, hey, that simplifies really nicely. But there's another simplification. You see this 2k plus 1 factorial? That is really 2k plus 1 times 2k factorial. So the 2k plus 1s cancel. So what we end up with is we end up with the sum k equals 0 to infinity minus 1 to the k divided by 2k factorial x to the 2k. And that is the power series for the cosine. We're done. You'll see in a very similar way, you see how we're like, well, we're altering, here we're alternating. There's x to the power divided by factorial, x to the power divided by factorial. Well, what's the difference? Well, notice in the sine, what kind of exponents did we have? We had the odd ones, because sine was an odd function. Well, what's true about cosine? Cosine is an even function. And what kind of powers do we have? We have even powers. So that says cosine is an even function. All right, good. So that matches with our expectations of what should be true. And this is just as important as the sine function is. So again, this is one that you should know. So this is cosine of x. All right, so what have we done today? Well, we had this idea that said Taylor series really is, what are we trying to do? Well, we're trying to match all the derivatives of the function at a point. Now, most of the time we'll do it at 0, but, and if we don't specify, assume it's at 0. We can do it at any point we want, 1, 2, it doesn't matter. We can do it. And by doing these approximations, we can start to extract lots of interesting information. We found the Taylor series for 3 important functions, e to the x, sine of x, cosine of x. We actually know the Taylor series for another important function, and hopefully you remember it. Spoiler, it's geometric. All right, good. Well, okay. So we're going to next time get into sort of understanding why are these good approximations, and then we'll start doing some applications. But that's for our future classes. We're done for today, and we'll see you next time. All right, bye.